Okay, what I want to talk to you today about is something called vapor pressure. And vapor pressure is, well, it's the pressure of a vapor above a liquid. I'm sure we've all had the experience of, let's say you've got a bottle of something here and it has a liquid that's liquid that evaporates easily. Maybe it's a nail polish remover. And if you unscrew the cap, we hear that noise. Pfft. Not sure how to spell that, but I'll call that PFFT. How's that? But we hear that noise. Pfft. And that's vapor being released. And we also know that if it is at a higher temperature, we know there's going to be a higher pressure. Well, in this video, I'm just going to look at why we get vapor above a liquid and what that pressure is going to be. So let's suppose that we have, let's say I have a liquid or a container here, a closed container, and I've got some liquid in there. Here it is. And let's consider a molecule in the liquid. As you probably know already, there are intermolecular forces between molecules. So let's draw 2 or 3. I don't want to draw too many molecules, but we have intermolecular forces, attractive forces between the molecules. And I'm assuming that you have covered intermolecular forces by now, but just in case you haven't, or if we want to review them anyway, we could say that there might be dipole-dipole interactions. There could be, well, there will be London dispersion forces. Sometimes these are known as van der Waals forces. And depending on what kind of a liquid it is, you might have hydrogen bonding. And all of these together constitute attractive forces, and we can just label them maybe as IAF, intermolecular attractive forces. So these forces are going on constantly. Molecules are always colliding with each other. So there are collisions between molecules in the liquid. And that causes molecules to move at different speeds. And these speeds are always changing. I mean, for example, if you consider a pool table, you hit a ball, it hits another ball, that ball speeds up, the one you hit slows down, balls go at different speeds. Well, this is happening with molecules all the time, and some speed up, some slow down. Well, in the interior of a liquid, such as we have here, molecules are attracted in all directions. So there they are. There are just attractive forces everywhere. But now, let's look at the surface of a liquid. So let's say that we have, here's another container, and we've got molecules at the surface. And again, they are being attracted sideways and down towards other molecules like this. And they're moving at different speeds, just like everybody else. And let's suppose that you've got molecules that are moving fast. Suppose you happen to have at a given moment a molecule or some molecules that are moving fast. Well, what's going to happen? Well, they can escape. They can overcome, let's put it that way, they can overcome the intermolecular forces at the surface due to the other surface molecules, and they can escape into the vapor phase. So they're escaping, and we'll show one escaping here. Here he goes. He's the one that got away. Okay. Well, there are many that got away. So they are escaping, and there would be what's called a rate of escape, or an escape rate. And that simply depends on the temperature, the size of the intermolecular forces. Won't get into that in this video. But we do have an escape rate, and that's constant. Okay. Well, now let's look. Let me get another piece of paper. Let's look at the molecules that are now in the vapor phase. So let's say here's our container, and we've got these molecules in the vapor phase, and they are literally, well, they're literally bouncing off the walls, and they're bouncing, colliding with each other. There are attractive forces, but there are collisions between these molecules. And so in the vapor phase, just like the liquid phase, these molecules speed up, they slow down. Well, let's suppose that a molecule at a given moment might be pointed in the direction of down. Well, if it's moving really fast, it might just bounce off the surface. But suppose it's moving fairly slowly. Well, a molecule that's at the surface will be attracted to the one that's coming down, and if it's moving slowly enough, it'll stick. Gotcha! And so it'll come back into the liquid. Well, let's think about this. As the escape rate continues, molecules are building up. They build up. The amount of molecules, or the amount of moles, if you like, build up in the vapor phase. And since there are more and more molecules in the vapor phase, then doesn't it make sense that the rate at which they're going to return to the liquid, well, that's going to build up as well. So we could say that the molecules return at an increasing rate. Number of molecules returning is increasing because the number of molecules in the vapor is increasing. So they return at an increasing rate. Well, the escape rate, as we said earlier, is constant, but the return rate is increasing. So doesn't it make sense that there's going to come a time when the escape rate, rate at which molecules escape into the vapor, is going to become equal to the return rate. And when that happens, we have what's called a dynamic equilibrium. Dynamic equilibrium. I guess in English that means everything's happening but nothing's changing. So there are probably numerous everyday examples of that, like your paycheck or something. But anyway, dynamic equilibrium. And so what that means is that the amount of vapor is fixed. The amount of vapor is fixed, which means that it has a fixed pressure, because the amount is fixed. Fixed pressure. And we call that pressure, this is called the vapor pressure. I'll just call that VP, vapor pressure. It's called the vapor pressure of the liquid. It's a vapor, but it's called the vapor pressure of the liquid at the whatever the temperature is, at the given temperature. And that's fixed. So that vapor pressure is fixed for that liquid at that temperature. It doesn't matter, science is science. It doesn't matter what part of the world you're in. So whether you're measuring a vapor pressure in Ireland, or if you've got a Scottish liquid, or even if you are in France and you have the liquid français, it doesn't make any difference. The vapor pressure will always be is the same.